One of the most interesting fields of research in parallel computer applications is signal and image processing. The use of transputers to implement high parallelism architectures and algorithms looks particularly promising due to the favorable price-performance ratio of these processors. In this framework, Department of Biophysical and Electronic Engineering research projects have two main objectives: the design and construction of a new transputer-based computation unit for high parallelism multiprocessor systems, the development of a workstation for image processing on transputer networks. Project development was performed on a Siemens personal computer acting as host and controlling the transputer subsystems. The transputers are interfaced with the host computer by means of standard motherboards. A transputer-based graphics board is also available for image visualization. A special project was set up with a view to increasing transputer connectivity. One of the results is a new transputer-based processing unit called a high connectivity node. In general terms, a high connectivity node is a virtual processor with more links than conventional transputers, so enabling the construction of more complex networks. The project began by placing two transputers on the same board and developing an interconnection technique that does not use their communication links. As all 8 links are therefore available for connections to other processors, the computational power of the new unit is theoretically double that of a single transputer. These characteristics are achieved by means of shared memory used as a communication channel between the two processors. Processes running on each of the two transputers can therefore exchange messages with 32-bit parallelism. The remaining components on the board provide the NMOS standard interface to the motherboards. Another important feature of the project is the complete transparency of the architecture with respect to tools available for implementing and debugging transputer-based network software. This degree of parallelism means that internal message passing is much faster than between two transputers communicating over conventional serial links. The two transputers, plus the shared memory, can therefore be considered a single, autonomous computing unit. Its high connectivity makes the new unit ideal as a processing element for implementing multiprocessor systems with many nodes and a particularly complex topology. Typical multiprocessor networks with these characteristics are hypercubes, graphs, multiplane grids. These configurations need many high connectivity nodes and employ their features to the full. The first software application to use the high connectivity node is in the implementation of simulation algorithms in the field of molecular electronics. One of the main aims in molecular electronics is the use of molecular assemblies as devices in molecular information processing circuits. From this point of view, lipid monolayers are realistic candidates as basic materials for molecular electronics. Lipid monolayers are the main constituents of any cell membrane. A lipid molecule can be modeled as a dipolar head covalently connected to a hydrophobic tail. The main feature of the lipid monolayers is the large number of interacting molecules and the local interactions between the hydrophilic heads of the lipids. The dynamic evolution of the lipid monolayer heads is based on a model of the interactions between dipoles. One of the main areas in which high parallelism systems are used is image processing, both for reasons of speed and the ease with which the algorithms are parallelized. One of the main data structures used in image processing is the two-dimensional matrix, which represents the spatial distribution of luminance values, coded as gray levels or colors, or associated to symbolic information. In most cases, executing an image processing algorithm involves the application of a set of operations to all the elements in the matrix. This can be performed concurrently in different parts of the image to achieve significant improvements in execution speed. The image to process is divided into 8 strips, with each strip being processed by a transputer in the network. The maximum possible improvement in speed is achieved using this strategy. In theory, speed is increased 8-fold, the number of transputers in the network, but in practice the figure is lower due to the time spent communicating between transputers. The strategy also exploits the maximum computational power of the transputer by reducing the number of communications between transputers and transferring large blocks of data for processing. The choice of the correct transputer network topology is crucial and must be based on the specific algorithm to implement. As it is not possible to connect the transputer root to all the remaining transputers, and in our case the root has only one free link, we adopted this tree network, which allows data to be transferred to all the processors in only 3 steps. The master task runs on the transputer root and handles the user interface, file handling, and above all the decomposition of the image to process into 8 strips, dispatching the strips to the network, and then receiving and recomposing the processed strips. The man-machine interface is totally user-friendly. The display is divided into 5 windows. Window 1 displays the items in the current menu. Window 2 displays system status, the names of the 5 images that can be stored in the video RAM stack, and the 2 images stored in the video buffers. Window 3 is dedicated to user interaction. Window 4 displays suggestions for user input or error messages. Window 5 shows the total time taken over the most recent computation and the mean, variance and histogram of the current image if this option is switched on. The slave G task runs on transputer TG and manages the B007 graphics board. This involves setting up the lookup table and displaying one of the 2 images stored in either video buffer 1 or video buffer 2. Each of the tasks running on transputers T0 through T7 processes a single strip of the image and in some cases concurrently switches other strips of the image to other slave tasks in the network. This strategy exploits the real parallelism between link interfaces, CPUs and FPUs fully and reduces the importance of communications in calculating the time spent processing a particular image. We will now show you the results of a number of types of image processing with an emphasis on low-level processing. These operations are called Grayscale Manipulations. The upper right image is the original, the upper left image is the original with an inverted grayscale, the lower right image is produced by thresholding with 3 thresholds, and the lower left image is obtained by expanding a range of gray levels to a different range. These operations are called direct histogram modifications, and the result is usually contrast enhancement. The upper right image is the original, the upper left image is the result of histogram equalization, the lower right image is the result of histogram hyperbolization, and the lower left image is obtained by specifying a triangular histogram. This set of images illustrates the effect of some noise reduction techniques. The upper right image is the original, the upper left image is the result of the convolution of the original with the 3x3 mask, the lower right image is the result of median filtering, and the lower right image is obtained using Nagao and Matsuyama's edge-preserving smoothing technique. This set of images illustrates the effect of some sharpening techniques. The upper right image is the original, the upper left and lower right images are the result of the convolution of the original with 2 3x3 masks, and the lower left image is the result obtained by so-called deblurring with the Laplacian. This set of images illustrates the effect of some edge detection techniques. The upper right image is the original, the upper left image is the result of edge detection using the Laplacian, the lower right image is the result of edge detection using the Sobel gradient, and the lower left image is the result of edge detection using the Kirsch compass gradient.